Hello and welcome to this video talking about this time Poisson's law. So we just finished with binomial distributions in comparison with hypergeometric distributions, and we saw that in certain conditions a binomial distribution could be used instead of a hypergeometric one. So now there exists another law, that is Poisson's law, that has been created to avoid the formula of a binomial distribution. So what is the problem with the formula of a probability in the binomial distribution? There is still a combination number, C and K. And in case of big samples with a little n, okay, it could be a problem for computers to calculate these combination numbers. So the French mathematician Poisson, approximately 1 century after the binomial distribution, and more than 1 century, researched a formula that could look like, in terms of results, of course, the binomial formula, but without using any combination number. And Poisson reached this result with his formula. So there are conditions in which you can use a Poisson's law instead of a binomial law. It's not always, in any case, that you could use this, but many softwares use Poisson's formula instead of binomial's formula. So let's read with you. In many cases, the number of different values that a variable x can reach is very big. So it's the case when the value of n, the sample, is very big. So the number of success could be between 0 and n. So calculating a probability may involve very large numbers of combinations and also include large powers if the law is binomial, that even a computer might not be able to calculate, or not correctly, or not at all. Moreover, in case a success is a rare event, every result isn't useful, like calculating the extremely low probabilities of many non-realistic situations, implying a large number of successes. So, what does it say? Okay, what's the meaning of this sentence? It means that if you're talking about very little chances of success each time you try your experiment, for example, you are trying something 200 times, and each time your chance of success is 1 over 100, 1% chance of success. So would it be a good idea to calculate the probability of having 100 successes after 200 trials? So no, it could be calculated, but it's useless. And more of that, some calculators would not be able to calculate your result. So it's good news for the Poisson's laws, because Poisson's law is very adapted to rare events, rare successes, and so low probability of success. In the context of a binomial law with a low value of p, another formula can be used instead of the binomial formula based on the Poisson's law, whose results will appear to be close enough to reality. And you can see that rare events, so rare successes, can deal with many concrete situations. So examining a sample taken from a large quantity of products or a large harvested production, in case the probability p can then an element is shoddy, so wrong is low. So if you talk about industrial production of boats, for instance, okay, or if you examine a harvest of apples or bananas and so on, you've got a very big population, and you have to take a big sample. Okay, the population is much bigger, but your sample has to be big in the goal to examine your production. Of course, you can't examine every single element of the population of the production. But if you want to forecast what your production is, roughly, you have to take a big sample. And the fact that something could be wrong in an element is quite always a rare event. Okay, if your industry produces boats, the fact that a boat is unusable consists in a probability of 1 over 100 or 1 over 1000. It's very a little probability of success. So you can read all of that. Okay, you can examine a big production. You can think about problems of length of a queue in a store, for instance. Okay, uh, the length of the queue depends on problems that could occur with a cashier. And this problem is not a likely event. Okay, it could be considered as a rare event. And thanks for us as customers. It's in the frame of the Poisson distribution. Predicting a maximum number of accidents or failures or other rare events concerning a large population for insurance companies, for instance. The fact that a house will burn this year is a rare event for each individual in a population. But for an insurance company, it has to forecast a maximum number of possible accidents. So maximum could be reached and then exceeded. But this insurance company has to forecast a maximum number of accidents thanks to Poisson's law formulas and the software that an insurance company uses takes it into account. Rare events inside large numbers. Okay, so that's a conclusion here. Rare events inside large numbers of clients, of objects, and so on is good condition for the use of a Poisson distribution. So let's take examples, of course, in order to calculate something. So in the context of a binomial or hypergeometric law under certain conditions, we can therefore use an approximate model as Poisson law, whose results will be fairly close to reality. So now let's establish a scheme between the three discrete probability distributions that we saw. We began with the hypergeometric distribution at singular, taking three parameters into account. Then we saw that with possible repetition or with a constant probability of success, that is the same meaning, we are able to use a binomial distribution with its own formulas. We knew in the former video that there was a possibility to use a binomial distribution instead of a hypergeometric one if we could consider that the size of the population was at least 20 times the size of the sample. Now, we will be able to use a Poisson distribution if some criterions are met. So there exists a P here for Poisson, and this distribution only uses one parameter, so we will talk about it, of course. What are the conditions in which a Poisson distribution could fairly represent a binomial one? There are actually three conditions. The first one is that the size of the sample must be more than 30. Then the probability of success must be little, and the limit has been placed to 0.1. Okay, so less than 10% chance of success. So n must be big and p must be little or low. And what of the two is more important? In fact, it's p. The product n times p mustn't exceed 10. Okay, so even if n is big, p has to be very, very low in order to the product n times p is not too big. If the three conditions are met, you are allowed to use a Poisson distribution instead of a binomial distribution. If one of the three criterions is not met, you are not allowed to use a Poisson distribution, and you have to use your binomial distribution. So now, what is the value of the parameter of this law that has to be used? In a Poisson distribution, the parameter is the expectation of the law, coming from, of course, the expectation of the binomial law, which was n times p. So lambda equals n times p here if you want to create a Poisson distribution coming from a binomial one. This way, there are formulas that don't contain combination numbers. So to obtain a probability of a certain number of successes, k successes, you will have to calculate the exponential of minus lambda times lambda power k divided by the factorial k, okay, factorial number of k. So there is still a factorial number, but in general, you're interested in low number of successes because you're talking about rare events. As we saw, lambda describes the expectation of the law, e of x equals lambda. And this way, the variance of x equals lambda as well. And then the standard deviation is the square root of lambda. So things are calculated in a very simple way with a Poisson distribution, and it's very easy for computers, even for a calculation of a probability. For computers, of course, not for us manually. So let's take an example with exercise 10. The law of the variable x is binomial. So let's talk and begin with a binomial distribution with parameters n equals 50 and p 0.06. Obtain calculators lists p of x equal k for each integer k from 0 to 7. So I wrote more than asked here in list 1, 0 to 10. So we will consider only 0 to 7. It's not very important. And you have to ask your calculator in list 2 the probabilities in the frame of a binomial distribution. So, of course, you will ask binom FDP to your Texas or binomial PD to your KGO with the right parameters, okay, with n, p, and the value of successes. And for a KGO, first the number of successes and then the parameters of the law. The results are these ones. You can see that the biggest probability is obtained for 3 successes. Would it be possible to forecast that the biggest probability would have been for 3 successes? Yes, because the expectation shows us the most likely event. And the expectation n times p equals 3 here, 50 times 0.06. Okay, that was just a comment. Now let's graph the probabilities with the law B50 0.06. So you can see that you've got a characteristic binomial distribution of probabilities. 7 to 8, 9, and maybe 10 here. Yes, 9 and 10 are very low probabilities. So you've got a kind of bell curve here, even if it's not a curve, of course, you've got bars, vertical bars. But you can see that around the expectation, that is 3 successes, you've got probabilities that are decreasing to the left and to the right. So a characteristic distribution. Okay, we just calculated probabilities in a binomial distribution. Now let's create a Poisson distribution and then let's compare results. Justify the approximation of this law by a Poisson's one and Rose parameter has to be given. So you have to know if you have the right to use a Poisson's law. So let's examine the 3 criteria. Is n more than 30? Yes, it's 50. Is p less than 0.1? Yes, it's 0.06. And is n times p less than 10? Yes, n times p equals 3. So the 3 criteria are met, and then you can use a Poisson distribution. Which one? The one whose parameter is 3, n times p. So the law B 50 0.06 can be approximated by the law P of 3. And now you can ask your calculator about results using Poisson FDP or Poisson PD, it depends on your calculator, instead of binomial FDP or binomial PD. But in the case of Poisson distribution, you have access to a table that could be given by your teacher, and that prevents you to use your calculator. So let's see the rest of the exercise. Give by using Poisson's law table the probabilities asked above. So we will see a Poisson's law table. Compare them to the ones obtained with the binomial law. So what a Poisson's law table look like in a paper sheet? It looks like that. You've got some considered parameters of different Poisson's law, and k as numbers of successes that can be considered. And there is no end for k, because in a Poisson distribution, whatever the distribution, the number of successes is virtually infinite. Okay, the Poisson distribution is created like that. Okay, the number of successes is a variable between 0 and infinity. So it's not very important for us, because the probabilities that are the most important here are the probability of low numbers of successes. So you just have to read the right column. In our example, we consider a parameter of 3. So we just have to look at this column. And then we just have to read the probabilities of the considered number of successes. In the exercise, it was from 0 to 7. So the probabilities are here. So let's write them in front of the probabilities of the binomial distribution. And of course, we can get them using the Poisson tool of the calculator, okay, like that. So you just have to try it on your calculator, and so do it in list 3 in order to keep the results in list 2 and then to compare them, like that has been displayed here. So we can see that the differences between all the results are not very big. Okay, there are very, very small differences. This is why the parameters, the criteria, sorry, have been met. Okay, and if we graph them, we can see that there are some differences, yes, but very little compared to each value. So the Poisson distribution as a characteristic that the biggest probabilities are a little bit lower than the reality, and the lowest probabilities are a little bit more or bigger compared to reality. Okay, so it enhances this kind of probabilities, and it makes the biggest probabilities decrease compared to reality or to the binomial reality. So it could be taken into account, but it's not an obligation, okay? Because if your criteria are met, you know that the differences will be little for any probability. So it's not a big problem for us. So now, if you want to calculate the expectation and the standard deviation, it's very easy, taking Poisson distribution, because it's just lambda or the square root of lambda. That's all. In a binomial distribution, it would be so 3 for the expectation, just the same value as in the Poisson distribution, and you would have to calculate the square root of n times p times q instead of the square root of n times p in the Poisson distribution. But q equals 0.94, and its square root is approximately 0.97. So multiplying something by 0.97 is not changing a lot the result, okay? And that's why we can consider that the square root of lambda is good to give us a good value or good enough value for the standard deviation, even if we are using a Poisson distribution instead of a binomial one. So of course we will see better how to use it and how to create it in the beginning with a video based on exercises. Okay, it will be the most important. Okay, so bye, and let's see us again with a new video.